Talk about circuits and what makes up a circuit. When something is wired correctly, this will cause electricity to flow through a circuit, which typically powers a lot of household items you're used to running by electricity. So this flow of electricity we call current, the flow of electric charges. When you hear this word current, I don't know about you, but I often think of water. And this is a really good analogy to use whenever you're solving these problems and whenever we get deeper into this. Think of this flow of electric charges as the flow of water. What does water do as it flows through a pipe or a straw or through a river? It's just a good comparison, or it's a really good analogy to use. But this current won't flow unless there's something called a voltage difference present. Maybe you're familiar with this word voltage. Whenever I hear voltage, I think of a battery. So there has to be a battery with some sort of potential difference present. And maybe you remember from chemistry that chemical energy is converted to electrical energy within a battery. This kind of gives the charges the push they need to move forward. So without this potential type of energy present, these charges won't flow. So this voltage difference they're talking about, there needs to be conductive material connecting one end to the other, but the difference is the positive end and the negative end. Charges flow from one to the other, and if there's conductive material connecting these two different ends, electricity will flow. Now think of electrons. Electrons are the moving charges in this case. Why are they the moving charges? Let's think back to chemistry, and I'm going to kind of zoom in up here where I have some space to draw. There are protons, neutrons, and electrons. Protons and neutrons can be found on the inside of a cell in the nucleus. The electrons are kind of floating around outside of the nucleus, and because they're on the outside of an atom, they're the easiest to move around, so those charges are going to be the ones that move. And they typically have a negative charge. Well, that negative charge is going to want to be repelled from the negative side of the battery and move towards the positive end. How fast or how quickly this happens is what we call current. So we can calculate current using this equation. We got some funky symbols and stuff going on here, so you're going to need to memorize or make some fun tricks for this. So the symbol for current is going to be capital I. And I know that doesn't really go together, but how I think of it, it's kind of a silly way, is that letter I, that capital letter I, looks like a wire or a river where current would flow. Silly, but maybe it'll help you. We measure current in something called amperes, or amps for short. Big capital A is the abbreviation for that. Q is also the symbol, a funky symbol, for how much charge we are talking about. It's measured in coulombs, the symbol for which is capital C. T is time, it's seconds, that hasn't changed. So you can see current is basically charge divided by time, how fast current is flowing. Don't get freaked out by this little bullet point down here. Ampere is what we call a derived unit. It's what we get when we divide coulombs by seconds, so we don't have to deal with complicated coulombs per second or anything like that. We just make it into amps. And electrons actually move fairly slowly through wires. So you would think they would move kind of fast because you think of it as light, but the electrons actually move slowly. Let's try some math. A current of 5 amps, you can label that current, flows through a copper wire for 20 seconds. That's a time. How many coulombs of charge pass through the wire in this time? They're asking us to find charge. Well, we just learned an equation that could help us out here. Current equals charge divided by time. So I'm going to go ahead and plug in the stuff the problem tells me. And to rearrange this to get Q by itself, I'll multiply both sides by 20. I get the amount of charge is 100 coulombs. Simple enough. So I'm going to talk a little bit more about the direction that current flows. We know that what's carrying the charge are the electrons, and the electrons have a negative charge. So there are a couple of different types of currents. Real current is what is actually happening, which we talked about earlier. Electrons will be repelled by negative and attracted to positive, so they'll actually move towards the positive end of the battery. But a long time ago, before scientists really knew which particles were the ones that were moving, they assumed things flowed in the opposite direction, away from positive and towards negative. So we're going to call this conventional current. And when we solve problems, we're going to actually treat the flow of charge as if it's going from positive to negative. That's the way it was done forever, and so we're going to continue to do it this way. And as it turns out, the math isn't going to be any different if we flip around the direction. So something to just keep in mind, real current goes from negative to positive, always. But what we draw in class is from positive to negative. Again, won't mess up the math or anything. The other thing to kind of keep in mind is what is moving in the wire is electrons, but the energy company doesn't actually send us electrons to move through all of these wires. Think about where electrons exist. Everywhere. Every atom has an electron in it, with special circumstances being the exception. But for the most part, natural materials and everything that you exist around you has a neutral charge, meaning that they have just as many protons as they do electrons. So electrons exist everywhere. All the energy companies give us is the energy to push these electrons through the wires and move them around in places where they already exist. So we are not getting electrons from batteries or outlets or anything like that. We are getting energy or voltage, okay? Speaking of voltage, this is just an energy source for these circuits. It's what causes these charges to move. Think about if you've ever looked at a battery, you feel a little spark because you've connected those two ends to each other. There needs to be a difference on either end of the battery, and if you connect it with conductive material, electricity will flow. Voltage is sort of nice because the symbol for voltage is big capital V, and it's measured in volts, which the symbol for which is also big capital V. The other thing needed for a circuit to work is something called resistance. And resistance is exactly like it sounds. It resists the flow of electrons. So really, anything that uses up energy, like light bulbs or motors or anything like that, is going to provide a small amount of resistance. Even the wire will have a teeny tiny amount of resistance, but for this class, we are going to assume it's so small, we are going to ignore it. But anything that uses energy, even a little, provides resistance, and that resistance is measured in something called ohms, the symbol for which is this little horseshoe symbol. So if all three things of these are present, we will have a circuit. Here are some other things that affect resistance. So I mentioned a moment ago that wire does have a teeny tiny amount of resistance in it. So it would make sense, the more wire I have, the more resistance to flow I would have. It'd be easier to get through a short hallway than a long hallway. You'd get through it quicker. Cross-sectional area is a fancy way of saying diameter. So basically, the wider a wire, the easier it is for current to flow, which should make sense. If you have a big wide straw, it's easier to drink your drink. If you have a big wide hallway, it's easier for people to pass through. The skinnier a wire is, the skinnier anything that provides a path is, the harder it will be for things to flow. Material and temperature also play a factor in this. Some of you might be confused about temperature because you think, well, if it's hot, it has more kinetic energy, so it should flow faster. And while that's true for a lot of other things, for electricity, it actually makes things more complicated. Think back to chemistry. I know maybe you've seen some simulations about what happens when you heat up a gas. A lot of those molecules just kind of jump around, and they end up applying a lot of pressure to the surface of the object. Well, that's what happens. They kind of all jump around on the inside of the wire, and they're not really causing it to flow forward in a uniform fashion. They're all just jumping around. And so it's actually harder to flow smoothly through something where everything's chaotic. Think about when you've had your computer overheat or your phone's very hot. It doesn't work as well. That's why temperature typically increases resistance with electricity. So again, circuits need to have all three of these things present in order to work. You need to have a voltage source like a battery. You need to have a complete circle of conductive material from one end to the other of the battery, needs to be complete. I'll abbreviate that I for current. And you need resistance. So you need all of these things for electricity to flow. Someone put it together in a math equation called Ohm's law. Ohm's law just shows the relationship between all of these, and it's actually pretty simple. If you look at the equation, current is equal to voltage divided by resistance, meaning current is directly related to the voltage. So the stronger my battery, the more current is going to flow. But the reverse is also true. The more resistance I have, the harder it's going to be to flow. So just kind of keep that in mind whenever you're doing some of these problems. Here is a kind of awkward picture illustrating the same point. Amps are the current that's trying to flow forward, and volts supply the energy to push those amps forward. But ohms provide resistance. They make it harder for that current to flow and proceed forward. So let's try a math question. How much current is drawn from a 1.5 volt battery in order to run a 0.5 ohm light bulb? Here, it's helpful to have your units memorized. So I know volts measure voltage, and then ohms, if I remember correctly, measure resistance. They're asking us to find current. So lucky me, I just learned Ohm's law. So I can plug everything into this equation. Voltage is 1.5 volts, and resistance is 0.5 ohms. If I type that into a calculator, I get current is about 3 amps.